Today's workshop is workshop number 3. We are going to work on our resonance. So we've done 2 lectures on resonance so far. Again, it's an important topic. And today will be a workshop fully dedicated to resonance. So let's hop right into it. Again, if you want to pause the video at any time to attempt the problems on your own, you're encouraged to do so. But if not, follow along with me as I work through them. Okay, so for the first problem here, let's just draw resonance structures. Okay, let's just draw resonance structures for the following molecules. Let's start off with a nice simple one here. Say we have an oxygen in a 5-membered ring, carbocation at this position. How would we draw a resonance structure for this? Well, we should notice that we have a lone pair adjacent to a carbocation. So we could take that lone pair and it could exist as a pi bond between that empty p orbital, that carbocation, and the oxygen. So those 2 electrons could be a pi bond there. That would give us this structure here with a double bond and then a positive charge now on oxygen. So those are the 2 resonance structures we could draw. If we wanted to draw a electron pushing arrow to go back to the starting material, we could take that pi bond and draw an arrow to oxygen, indicating that those 2 electrons in the pi bond could also go back and be a lone pair to go in the reverse direction. Okay, so those are the 2 resonance structures that we could draw for that structure there. Okay. Nice and easy. What about this structure here? What if we had a carbon chain with a nitrogen, double bond here, lone pair on nitrogen? Okay. What could we do here? Well, we should notice that we have a pi bond, a double bond, between atoms of differing electronegativity, right? We have a polar pi bond. So we could draw this pi bond as a lone pair on nitrogen, since nitrogen is more electronegative than carbon. That would give us this structure here where we have, remember, you're never changing the single bonds. It's only the pi bonds and the electron lone pairs. Okay, so nitrogen now has 2 lone pairs. Nitrogen has a negative formal charge, remember? And this would be a carbocation. Okay, so that would be the resonance structure we could draw. We could draw the reverse arrow to go back to the starting material. That lone pair could come down to make a pi bond. Okay, so those are the 2 structures we could draw, the 2 resonance structures. Again, sometimes you'll see them in brackets. I don't mind if you put them in brackets or not, but those would be the 2 structures that we could draw there. Okay, next. What about this one here? What if we had a 5-membered ring? With an oxygen. Okay, this is called a lactone. A lactone, if you have a C double bond O with an oxygen in a ring system. So if we have this lactone here, what are some resonance structures we could draw? Well, we should first off note that we have a C double bond O. We have a polar pi bond. We also have some lone pairs in the allylic position. Okay, so we have a couple different things we could work with here. Let's start off with the pi bond. That should be a nice easy one, where we just pop that pi bond up to be a lone pair. If we do that, that gives us our 5-membered ring untouched. We now have a single bond here. Oxygen will have 3 lone pairs, giving a negative charge, and that carbon is now positive since we took 2 of its electrons away, 2 of its shared electrons. Remember, all your charges should balance out. We have a neutral charge, and then we have a plus and a minus, so a neutral. So that looks good. Now we could bring this electron lone pair back down to make a pi bond, right? That would give us our starting material. But let's take these electrons over here and make a pi bond instead, because that would give us a new resonance structure, which we'll draw over here on the right. That would put a double bond down to this oxygen instead. Single bond up top. This oxygen is still negative. This oxygen down here has 3 bonds now and 1 lone pair, so it's positive. Okay, overall neutral. So that would be our final resonance structure that we could draw there. Okay. If we want to draw arrows going back to the starting material, we could draw these cascading arrows where we bring a lone pair down. That gives this carbon 10 electrons, so we'll bump this one out to be a lone pair up on oxygen. And if we follow those arrows, that would give us back our starting material here. Okay, so these are the 3 resonance structures we could draw for that molecule there. Okay, let's look at a structure that might have a few more resonance structures. Okay, let's consider if we have a 7-membered ring put a C double bond O here, double bond, double bond, double bond. Draw all the resonance structures for this molecule. So we have a lot of double bonds, and it looks like they are alternating. Double, single, double, single, double, single. So that means they're probably going to be in resonance, okay? Let's start with the first one, the nice easy, put the pi bond up as a lone pair on oxygen. That would give us our 7-membered ring. 7-membered rings are a little tricky to draw. Okay, that would give us a single bond there. Oxygen would have 3 lone pairs and a negative. Carbon would be positive. Then we have our double bonds. Now, we should see after that, now we're left with an allylic carbocation. An allylic carbocation. That's a carbocation here adjacent to a double bond. So that looks like it's a good contender for resonance. We can take those 2 electrons in that pi bond and we can put them over to fill up that empty p orbital over there. Those 2 electrons are in resonance here. They're delocalized and they can hop right over and fill up this position instead. So let's draw that. So that would put a double bond at this position. We took electrons away from this carbon. It used to have a double bond. Now it doesn't. So that carbon is positive. And then we have our oxygen here, which is the same. Now we can take this double bond and kick it over to here and move that pi bond over 1 position. That would give us this structure here. And hopefully you're now recognizing the pattern where when we have these alternating double bonds, we can kick each one over every single time. So alternating double bonds are typically in resonance, okay? So that gives us a positive there. We have a double bond at this position. And we can finally take this double bond and kick it over. That would give our 7-membered ring Oxygen, make sure your charges are all balanced. It looks like we have a plus and a minus on every structure, which is good. Double bond there, and then a positive charge on that carbon that we took the double bond away from. Okay. Now we should note that this, I'll draw it on our initial structure here. We have an sp3 hybridized carbon right here that has 2 hydrogens. So there's no resonance that can occur up here, right? We can't move the double bonds over here. We can't draw an arrow like this or like this because that's an sp3 hybridized carbon. So those are bad arrows, right? We can't just give an sp3 hybridized carbon like that an extra bond, right? We can't break a CH bond to make space for it. Remember, we can't break single bonds and we can't exceed the octet rule. So sp3 hybridized carbons will not participate in resonance. Only these sp2 hybridized carbons will. Let's highlight them in red. Remember our chapter on hybridization? sp2 carbons have double bonds. See how all of these carbons in red have double bonds? And all of those carbons in red are participating in resonance. They all have delocalized electrons. Okay, so it's very important to be able to recognize those sp2 hybridized chains, those sp2 hybridized carbons, and see where those pi electrons are going to be able to go. Okay. So these would be all the resonance structures that we could draw. Now I'm just drawing one arrow at a time because it's, I think, easier to see and learn that way. But you could also draw cascading arrows. So what I mean by that is, to get back to our starting material here, I could take a lone pair, turn it into a pi bond. When I do that, this pi bond needs to bump over one. When I do that, this carbon gets 10 electrons, so we have to bump over another pi bond and another pi bond, and you keep bumping them down until it's in a comfortable place, which would be filling up this empty p orbital, right? And alternately, on our first structure, I'm going to erase a few things here. Okay. If you need to look at that a little longer, you can go back in the video and pause. So alternately on our first structure, we don't have to draw individual arrows one at a time. For your first structure, you could do this. You could go, well, I'll bump this double bond over. I'll dump this double bond over. Boom, boom. And you can draw your first structure like that. Doesn't matter what order you draw them in. I'm just drawing them by moving one set of electrons at a time. But you could draw this cascading process. You could draw all the arrows together like that, where this double bond is sort of initiating that chain reaction, kicking those electrons all the way up. Or you could just start with that first arrow right here and just work your way down. Either way, totally fine. Ultimately, you'll get the same structures. Then you could move the double bonds around as you see fit. You could draw it again as a cascading process with these 3 and then 2. It doesn't matter how many you include as long as you're getting unique structures each time you draw. Okay. So in order to do that, I think it's easiest to move one set of electrons at a time. But if you think it looks cool to draw the cascading arrows, you're perfectly fine to do so. Good practice too. Okay, let's see. Let's draw the resonance structures and rank them. So we're going to rank them based on their overall impact now. Let's take a look here. Let's do this structure here. HO NH2 okay. take this molecule here. Let's draw all the resonance structures and rank them. So this is our first structure. It's just the molecule that we have. What can we do here? Well, we definitely have a lot of lone pairs next to a pi bond. We have our polar pi bond. Let's start by breaking that polar pi bond and draw our first resonance structure, which would be single bond here, oxygen with 3 lone pairs and a negative, carbocation and NH2. Okay, so that's our first arrow. That's our first structure we could draw. Now we have a carbocation adjacent to lots of different lone pairs. We could bring any of these lone pairs down to make a pi bond, right? Let's do, obviously not the oxygen on top, because that would just give us our starting material back. Let's take this oxygen first. You could also take the nitrogen, that's fine. Let's draw another unique structure here that gives us a double bond to this oxygen. That makes that oxygen positive. Then we have our negative oxygen up here with 3 lone pairs. We didn't touch that. That would be our third structure. And our final structure would be obviously making a double bond to this nitrogen. So we could either go back to this structure in the middle, and we could draw this arrow. I'm going to work with our structure on the right here. I'm going to draw this electron lone pair coming down to make a pi bond, and kick this pi bond up to oxygen back to a lone pair. So I'll draw those cascading arrows showing that this lone pair on nitrogen is coming down to make a pi bond. When it does, that gives this carbon in the middle 10 electrons, so it's going to bump this pi bond back to oxygen as a lone pair. Okay, that will give us double bond to nitrogen, NH2, which is going to be positive. Oxygen on top is still negative. That looks like all the structures we could potentially draw, right? Looks like we've exhausted all of our options. So we have 4 structures here. Now let's rank them. Okay, let's rank them now. How should we do this? Let's label them A, B, C, and D. Let's call this one A, B, C, and D. Okay. Right down here, let's consider our rules. Rule 1, Rule 2, Rule 3, and then if we need Rule 4, we'll come back to it, although we most likely shouldn't. Okay, so Rule 1, remember, is we want a filled octet. We want as many filled octets as possible. Okay, so considering our structures A, B, C, and D, which ones have filled octets? A does, B does not. B has a carbocation in the center, that's a 6-electron carbon. C has all octets, and D has all octets. Okay, so that looks good. Let's take a look at rule number 2 now. Remember, rule number 2 states that resonance structures that have the fewest formal charges are the best, that have the most impact. So if we consider all of our structures, B, C, and D all have 2 formal charges. A has 0. So A is going to be our best there. It has 0 formal charges. All the others have 2. Typically, when you have a neutral molecule, it's going to be your major resonance contributor. Okay, that's a little giveaway. Okay, and then we have rule 3. Rule 3 states that our negative charges should be on the most electronegative atoms. In this case, between oxygen, nitrogen, and carbon. Oxygen is the most electronegative. It's the most upper right on our periodic table. So let's look at all of our negative charges. The negative charges in every single case is on oxygen, right? So rule 3 is not really helping us out here. So rule number 3 is not going to be much help. Therefore, our best resonance contributor is going to be A. So let's put number 1, 2, 3, 4 in red. So this is our best resonance contributor. Our lowest resonance contributor is obviously going to be B. B. Okay, and then we have a tie. C and D are both very similar, right? C and D are both very similar. Okay, so what we're going to do to figure out which one is better, C or D, which one of these is a better structure since they're tied for rule number 1, rule number 2, we're going to tack on a little extra tidbit to rule number 3. And that is, so remember rule number 3 states that we want negative charges on the most electronegative atoms. We also want positive charges preferred to be on the more electropositive atoms. Okay, sort of the inverse of rule number 3. Positive charges preferred to be on the more electropositive atoms. So in this case, we actually do have a difference in the positive charges. We have one on oxygen and we have one on nitrogen. Oxygen is more electronegative, which makes nitrogen more electropositive, right? So therefore, this positive charge would prefer to be on nitrogen. So that's going to be a little better. So we'll call that 2. And we'll call this one up here C3. Okay. So that's just a little addition to rule number 3. It doesn't come up very often, but if it does, there you go. Usually you'll be considering the negative charges, but once in a while you'll have to consider the positive charge. Okay. So negative charges prefer to be on more electronegative atoms. Positive charges prefer to be on more electropositive atoms. Okay. Okay, so let's now look at an example where we have to determine if our lone pairs are localized or delocalized. That's something we finished off with last lecture. Let's take another look at that. So let's determine if the lone pair is localized or delocalized. And I'll draw some structures here. Let's start with this one. Nitrogen, 6-membered ring. Localized or delocalized? So remember, when we're asking localized or delocalized electrons, we're asking, are those electrons in resonance or are they not in resonance? Here they are in resonance because we could draw this lone pair as a double bond between nitrogen and that positive charge to give us this structure here. So we have a resonance structure we could draw. Therefore, those electrons are delocalized. Delocalized electrons because they are participating in resonance. Okay. What if we had this structure here? Resonance, no resonance? Is this lone pair on nitrogen localized or delocalized? Okay, this lone pair, maybe we could draw coming down here to make a pi bond between the positive charge and the nitrogen. But remember, when an atom has both a lone pair and a double bond, typically just the double bond will participate in resonance. So a better arrow to draw is take this set of electrons and put it over as a double bond here. Okay. Remember, when we have something like this from our last lecture, when we have something like this nitrogen that has both a lone pair and a pi bond, this lone pair is in an sp2 orbital. It's not in a p orbital. This pi bond is in a p orbital, right? That pi bond is in a p orbital. This lone pair is in an sp2 orbital. And remember, the delocalization of electrons, resonance, is occurring in those p orbitals. Okay. So this lone pair is actually localized, meaning that it is not participating in resonance. What is participating in resonance? This double bond, those two electrons right there. Those could hop back and forth between that positive charge on the left, positive charge on the right. It could be a pi bond in either direction. But those that lone pair of electrons on nitrogen, that's staying put. Okay. What about this structure here? Localized or delocalized lone pair? This lone pair, can it participate in resonance? Yes, it can, because we have an adjacent double bond here. We could draw this lone pair coming down to form a double bond and bump this double bond over to the very end to put a negative charge, a lone pair on that very last carbon. Double bond here. Nitrogen with 4 bonds is positive. So there's our resonance structure we could draw using that lone pair. So therefore, that lone pair is delocalized. Now, could we draw a resonance structure in the other direction? No, because we have this sp3 carbon in the way of that double bond. We can't jump over those sp3 hybridized carbons. Those sp3 hybridized carbons do not participate in resonance. It's only those sp2 carbons because we need that p orbital. Okay. Okay, let's look at an example here, sort of an application question. I'm going to draw a structure, and what we're going to do is determine all the sites of low electron density. Determine the sites of low electron density on this molecule. How are we going to do that? We're going to use resonance structures and resonance theory here to do so. Let's draw this molecule. We have a 6-membered ring. Okay, so we have this molecule here. We have lots of conjugated double bonds. When I say conjugated double bonds, I mean alternating, double single, double single, double single. Typically, when you see these conjugated double bonds, these double bonds that are alternating, that means there's resonance. Okay. So let's determine all the sites of low electron density. How are we going to do that? We are going to draw resonance structures and see which carbons have positive charges on them. Our most basic resonance structure we could draw is by moving that pi bond up to be a lone pair. That's going to give us a negative charge on oxygen and a positive charge on this carbon here. So already we've identified one carbon that has positive character. In other words, low electron density. Anything that we have a positive charge on, it's going to have low electron density around it. Because remember, resonance structures, all of the possible resonance structures we could draw, all summed together, give us an idea as to the overall electronics of that molecule. So anywhere we have a positive charge, there's some positive character in that atom. Okay, so we've identified one. How do I identify the other ones? Just continue drawing your resonance structures and see where those positive charges might end up. Let's move this carbon over. That will give us another positive charge on this carbon here, double bond. Then we have our oxygen. We can move over another double bond, and you're just going to work your way all the way down the chain here, moving double bonds and figuring out where those positive charges will end up. Okay, so now we have a double bond at that position, double bond here. And then we'll bump over another double bond. Once it starts to get repetitive and boring, that means you're starting to grasp it pretty well. So hopefully after drawing all of these, it gets a little repetitive. That's good. Okay, we have double bonds here, here, and then we have one double bond left that we can bump over. That would leave us with one more positive charge, double bond here, double bond here. And positive here. Okay, so there's all the resonance structures we could draw. Let's highlight all the carbons that have positive charges on them using red. So I'll draw it on the first structure here, the base of the carbonyl, the C double bond O. We also have a positive charge on this carbon here, and you'll start to see a pattern. It's alternating. Every other carbon has low electron density. Okay, every other carbon, all these carbons in red, we can draw a positive charge on them using resonance theory, using our resonance structures. Therefore, those carbons we know have partial positive character. Okay, that red color here means those carbons are partially positive. Okay, maybe not a full positive, but a partial positive, because remember the electronics of the system, it's a sum of all of these resonance structures. In most of the resonance structures, these carbons are just double bonds, right? But in at least one, these red carbons have a positive charge on them. Okay, therefore it's partially positive or low electron density. If you're drawing resonance structures where negative charge is moving around, that means anywhere you draw a negative, we have high electron density. Okay, in this case, the negative charge was just stuck on that oxygen the whole time. Okay, we're not moving that negative charge anywhere else. But in other structures, it will move around, and you can figure out where you have high electron density. Okay, so that's one application of resonance and sort of why we're learning it. Okay, let's finish off here with one last question, which will be sort of a challenge question, another application question, as we move into our next unit. So we will be talking about this next lecture or the lecture after that. I'm going to ask you this question: which hydrogen is the most acidic. And I'll give you a hint. Which hydrogen leaves behind the most stable negative charge? Which hydrogen is most acidic? Another way to say this is which hydrogen leaves behind the most stable negative charge? Okay, let's draw a structure here. Oops. Six-membered ring, alternating double bonds. We have a OH here. We have an OH here. And remember, we also have a hydrogen at each of these positions. I'm going to draw them all in. And on this carbon here, we have two hydrogens. So I'm just drawing all of our hydrogens in so we can see them all. Now, which hydrogen is the most acidic? Which hydrogen leaves behind the most stable negative charge? Now, we have to remember here that resonance is a stabilizing force. Resonance is stabilizing. The more resonance you can have, the more stable something is. Okay? The more resonance you have, the more stable. So a negative charge that's participating in a lot of resonance is very stable. Okay? With that in mind, let's just look at some random hydrogen. Let's take this one down here in red. Now, we'll talk about acid-base theory. That's our next chapter. So we're going to talk about it soon. But when we pluck off this hydrogen, if we take this hydrogen in red and simply remove it from the molecule, it's going to leave behind those two electrons in that bond. See that bond right here in black? This bond has two electrons in it. If that hydrogen gets plucked off by a base, it leaves behind those two electrons. So I'm going to erase that as if it were to leave from a base. And if those two electrons are left behind and we remove that hydrogen, that's what we end up with, a negative charge where it was. Okay? If we put a negative charge at this position by deprotonating or removing that hydrogen, is this a stable negative charge? In other words, does it participate in resonance? No, it does not, because there's a sp3 hybridized carbon here, and we can't draw any arrows towards that sp3 carbon. We can't break any of the single bonds on that sp3 carbon, so there's nothing we can do with it in terms of resonance. Okay? Therefore, that is not a very acidic hydrogen. Okay? That's not our best hydrogen. What if we pluck off this hydrogen up here in red? Let's take this one. If we remove this hydrogen, if we remove that, then we are left with a negative charge at that position. Is this negative charge participating in resonance? Well, it's adjacent to a double bond, right? This double bond down here, we have a lone pair adjacent to a double bond. However, remember, when you have a lone pair and a double bond on the same atom, just the double bonds will be participating in resonance. These are participating in resonance. Those are what's in the p orbital, right? These two electrons in these pi bonds are in the p orbitals. That's what's participating in resonance. This lone pair out here is in an sp2 orbital. That lone pair does not participate in resonance. Therefore, that lone pair is not acidic. That hydrogen does not want to leave, does not leave behind a stable charge. So let's look at this hydrogen here. Let's take this one off that I just circled. If we pluck that hydrogen off and leave behind a negative charge, leave behind those 2 electrons, we have this. This is a very good looking negative charge because we can draw resonance structures, right? We can draw a resonance structure where this lone pair comes down and we can make a pi bond here and bump over this pi bond. We can either dump it off here as a lone pair, or since there's another double bond in conjugation, bump these double bonds over as well. Okay, I'm going to start by just dumping these off as a lone pair, just so that it's nice and clear. So that would give us a double bond here. Oxygen would now be neutral. We would have a lone pair and a double bond there. Which would give us this resonance structure here. We could then take this lone pair, right, which is in a p orbital, because remember this hydrogen is still here. We could then take this lone pair and make a pi bond, and then turn this pi bond into a lone pair. And we can continue all the way around those double bonds, drawing resonance structures. So therefore, I'm going to draw our original structure up here. Therefore, this hydrogen right here that I circled is the most acidic hydrogen because it leaves behind the most stable negative charge. It leaves behind the most stable negative charge because when we form a negative at that position, that negative charge is delocalized. It participates in resonance all the way through that ring system. We can draw multiple resonance structures using that negative charge. Therefore, that negative charge is very stable. Therefore, that hydrogen is very acidic. Okay. Again, we'll cover acid-base next time, so that might make more sense after we talk about that. But as long as you understand that this negative charge right here is good, this is a good negative charge because we can draw lots of resonance structures with it, that's good. And hopefully you can follow along with the arrows as well. I'll continue drawing the rest of these resonance structures just for clarity. So we could put that negative charge at this position. That'd leave us with this. And we could move this lone pair to here next, and then put a negative charge up on that last carbon there. That would be all of our resonance structures. Negative charge out here, double bond, double bond, double bond, and our pendant alcohol out here. So we have 1, 2, 3, 4 resonance structures we could draw. We could also, let's take in blue, draw all of our atoms that have high electron density. These blue carbons have high electron density. If we were to deprotonate that molecule, take that hydrogen away and make that negative charge there. Okay. So those blue carbons, well, even if we didn't take off the hydrogen, those blue carbons have high electron density. Why? Because of the resonance structures. Okay. So there was a lot in that question. That was a good challenge question. If you can complete that question and you followed along well and understood it, then you're in great shape. If not, hopefully you at least understood the more elementary problems that we did previously. Those are key to understanding a lot of future chemistry. As you saw, I sort of introduced resonance as it applies to acid-base theory here, and we will continue using resonance in almost every chapter from here on out. So make sure you understand these key fundamental concepts in resonance. Make sure you understand that it's a stabilizing force. Make sure you understand where those electrons could possibly go when we have delocalized electrons and how we can draw those resonance structures. Okay. Okay, that's all I have for workshop number 3. I hope that was helpful. Resonance is a tricky topic. It's a little obscure to learn it at first, so I understand that. If you're still shaky on it, rewatch those videos, lectures 6 and 7, rewatch the workshop, and you can practice some more problems from your chemistry book, whichever one you're using, or elsewhere online. There's a lot of good problems. But I think it's very important to make sure you have a good solid foundation of resonance moving forward. It'll definitely help you. Okay. Okay, thanks for joining me, and I'll see you in the next lecture.